All right, at 4.5 and 4.6, we're going to look at concentrations for solutions and then using those concentrations of solutions to figure out some stoichiometry problems and some titrations that we're going to deal with here. So first thing is a reminder about concentration. Okay, concentration, remember, we deal with molarity. All right, so big M, so many moles per so many liter. When we talk about a stock solution or a standard solution, it's a solution whose concentration is known accurately. So if I'm talking about a standard, that means that's usually one solution that I made up for you. There's going to be some set molarity, okay? Now when we deal with this electrolyte, I deal with these concentrations, and we looked at this before, okay? The concentration of your ions depends on the formula. The more ions you have, the higher concentration. I don't think I brought it up before, but those right there, those little brackets mean a concentration. So if you would say, like, instead of saying 0.2 molar, people will oftentimes say the concentration of HCl is 0.2. Now I tend to also want to put the M underneath it, but brackets do mean concentration, okay? Like I said, the more ions you have, the higher the concentration. So for example, what are the molar concentrations of each of the ions present in 0.025 molar solution of calcium nitrate? So calcium nitrate is Ca, NO3, 2, because calcium is a 2 plus, NO3 is a minus. So if my overall concentration is 0.025 molar, that means I'm going to have one Ca2 plus floating around in my solution, and 2 NO3 minuses floating around in my solution. So I'm going to have twice as many NO3s floating around as you do CAs. So I have 0.025 molar for the Ca, and then it'd be 0.050 molar for the NO3, because I have twice as much there, and that's really it. All right, we did this in the sports drinks lab. Okay, we're dealing with dilutions. Okay. You're going to purchase a stock solution and then dilute it to a desired molarity. So I'm going to go from, say, a 2 molar solution down to a 0.01 molar, or a 14 molar solution down to a 2 molar. Okay, you're diluting the stock solution. And again, remember, diluting means that you are adding water. Okay? So what happens, though, to the moles of your solute when you're doing a dilution? Your number of moles stay constant. Because all you're doing is adding water. I am not adding more of the actual stock stuff. All you're doing is adding more water molecules to it. So that means the number of moles of the stuff that I have always stays the same. I'm not adding more of the moles of stuff, I'm adding more waters around it, trying to get it to be more dilute. If you remember, molarity is moles over liters. Well, if this mole number isn't changing from a before and an after, so this is my before, and then my molarity after. Okay, if this number here is staying the same, then we can just say, okay, well that means that it's really a constant. So my molarity times my volume is equal to my molarity times my volume. That's where we get the M1V1 equals M2V2. Okay, the molarity and the volume before multiplied equals the molarity and the volume after. Again, because your moles of the stuff stay constant, you just add water to it. So for example, how many milliliters of 3 molar H2SO4 are needed to make 450 milliliters of 0.1 molar H2SO4. What's nice about these is it is a before and an after, so units don't terribly matter in the sense that it doesn't matter if I have milliliters or liters, because the before and the after, you're not dealing with the mole number, okay? So if I have 3.0 molar times some volume, and I'm going to make 450 milliliters of 0.1 molar. So I'm going to need some small number of the 3 molar to dilute it down to 450. So all you do is you take these two multiplied, okay, and then I divide by the 3.0 molar, and I should come out to be 15 milliliters. You would take 15 milliliters of the 3, okay, so I got my little beaker here, all right, I want to have 450 milliliters total. I would only need 15 milliliters to go in there to make that whole total. Now be careful, because I should have said it like that. The 450 includes the 15, all right, not 450 plus 15. Well, again, you're just diluting it. And that's basically 4.5 of solutions and your concentration. Now we deal with 4.6, we're dealing with stoichiometry, so we're going to do a little bit of math, okay, where we use our molarity instead of moles or grams that I give me to start, okay? So all you got to do, you write the reaction. You're going to calculate the moles using a molarity and a volume, because remember, molarity is moles per liter, which means these two multiplied equal my mole number, okay? I'm going to determine a limiting reactant, and calculate the mass of some unknown. That's what you do for precipitation reactions and acid-base reactions. Okay, so it's stoichiometry that we did last year and the beginning of this year, just with a different beginning, is all it really is. Okay, so we'll look at an example here. I have aqueous solutions of Na2SO4 and PbNO3 that are mixed, and PbSO4 precipitates. I'm going to calculate the mass of PbSO4 that's formed when I have those two amounts of my solutions that I start with. So the first thing you want to do is, like I said in the last thing there, write the reaction in case it's not 1-to-1. Plus it helps you see the reaction out. So I am doing PbNO3 2, and I'm adding to that Na2SO4, and I'm going to form PbSO4 and NaNO3. I need to balance here, so I should have to have 2 here, and it should be done then. So now I look at what I've got. Okay, I'm trying to find, we'll do red here, I'm trying to find this PbSO4 and some number of grams. Well, what do they give me? Well, instead of giving me grams like we did last year for doing these limiting reactants, I have amounts in solution. So I have 1.25 liters and 0.05 molar, and I have 2.0 liters and 0.025 molar. So how are those two going to help me figure out how many grams I need? Well, if I need grams, means I need moles. If I need moles of my product, I need to figure out how many moles of my reactants I started out with. So that's where you have the next step in there. We have a liters and we have molarity for both. You multiply, that should give you your mole number. So 1.25 times 0.05 gives me 0.0625 moles. And the Na2SO4, 2 liters times 0.025 gives me 0.05 moles. Okay, it's 1-to-1. That's what